So today we're going to be discussing acid-base models and acid-base reactions. For the higher levels, there's three acid-base models you're responsible for knowing. For the standard levels, it's only two, which are the Arrhenius model and the Bronsted Lowry model. Let's start with the Arrhenius model. The Arrhenius model is only really applicable in aqueous solutions. An acid is a solution that contains H plus that produces H plus ions when dissolved in water, and Arrhenius base is a compound that produces OH ions when dissolved in water. That's the neutralization reaction. Pretty simple, really. So let's move on. The Bronsted Lowry model, however, it works. It's similar in the fact that it involves hydrogen. Um, it involves hydrogen changing hands and whatever, but it's broader than the Arrhenius model. Um, so it involves the transfer of protons. So a Bronsted Lowry acid is a proton donor, and a Bronsted Lowry base is a proton acceptor, or H1 plus. Note that H plus is actually a proton. We don't mean like protons from the nucleus. Since the most common isotope of hydrogen is just 1H, it has one proton, one electron, and no neutrons. So therefore, the 1 plus ion of hydrogen is just a proton. So just in case that was going to be an area of confusion, it shouldn't be. So, like I said, Bronsted Lowry acid is a proton donor, and Bronsted Lowry base is a proton acceptor. Let me fix my mic here. Sorry about that. The next thing I want to mention is conjugate acid-base pairs. So, acid-base reactions, if there's a Lewis acid, there's a Lewis base. You cannot have one without the other. It's more or less the premise. Like, in a proton transfer, you can't just have leaving and then donation and acception. They happen simultaneously. Something donates to something that accepts it. Now, we can track this. We can track the donation and acception using conjugate base pairs. Conjugate pairs. So, a conjugate acid is a pair whose formulas differ by one H plus, and the conjugate acid has one more H plus. A conjugate base is very similar, except it has one less H plus, or it has more OH minus. So here, for example, we have acid base. This is the conjugate acid of this base. It has NH4, only differs by NH plus, and similarly this only differs by NH plus. This has one more H plus, so it's an acid, so it's a conjugate acid, and this has one less H plus, so this is a conjugate base. There are established formats for showing generally the way you write an acid is you write what we call acidic hydrogens like separately from other hydrogens. So for example, for a carboxylic acid, generally you'll write down CO2H, where that indicates where the acidic hydrogen is, and these H's here, this is a carboxylic acid. This H is actually the proton that can be donated. These are just these are not. These are irrelevant. For simple acids and oxyacids, you can just write those polyatomic ions that you remember. You could just add H's to them to get their acidified versions of them, to get the acids. So hydrochloric acid is HCl, which Cl minus there. Sulfuric acid is H2SO4, which 2 times H plus and SO4 2 minus. For simple bases, the conjugate acid is usually written by putting an H in front of the base formula. So CN1 minus becomes HCN. This becomes ethanoate ion becomes ethanoic acid, and then water becomes hydronium. Lastly, we should mention the difference between amphiprotic and amphoteric species. An amphoteric species can basically act as both an acid or a base, and an amphiprotic species is a subset of something that is amphoteric, which means it can either donate or accept a proton. So an example of something that is amphiprotic and amphoteric is water. Water can act as a base, so here we see its water is acting as a base, it's accepting a proton from HCl, or it can act as an acid, where it'll donate one of its protons here to form NH4 plus and OH minus. Just checking the time here. All right. Now that we sort of have some basic terminology underway, now let's move into acid-base, reactions. So generally, if we're writing just acid, if we're just writing a generalized acid, we just use HA or H2A or whatever. And generally, the acidic hydrogen is attached to a significantly electronegative element. So it's attached to a very highly electronegative element, such as oxygen, nitrogen, or fluorine. That's generally the stuff that's generally used for hydrogen bonding. You can generally consider those as highly small electronegative elements that would be making acidic hydrogens. Acids are generally molecular, however, they behave quite a bit like ionic compounds in some manners. So, for example, they dissociate in water, meaning that their ions split. So, generally, for example, HA splits into H plus and A minus. You could use the Arrhenius model to justify this. However, what actually happens is this is the actual acid ionization equation, where HA plus H2O makes H3O plus and A1 minus, generally. So this is what actually happens. Now, for the higher levels that, we'll be studying quite a bit more acid-base chemistry, you do generally tend to, simplify it like this, and you'll get Ka and Kb based off this expression here. However, keep in mind that this is actually what happens. This is more or less what is actually happening. So the acid is transferring a proton to the water, or in the case of a base, the water is donating a proton to the base to make its conjugates. Water is amphoteric, as we just noted, like a few minutes ago. But when it reacts with a base, it acts as an acid, and when it reacts with an acid, it acts as a base. So generally, what you put into it determines how water will react. H plus itself is never actually in water. It's generally hydronium, H3O plus. It's a simplification. The reality is that protons are very small, and because of that, they just tend to bond onto lone pairs. They just form a diative covalent bond or coordinate bond with one of the lone pairs on oxygen and the water molecules to form H3O plus. That's sort of what happens generally. We can now we can categorize acids a bit more. Let's get into some more general categorizations. So we have monoprotic acids and diprotic acids, or polyprotic acids as they should technically be known. Monoprotic means only one acidic proton. Polyprotic means multiple acidic protons. Oxyacids are the fully protonated forms of the oxyanion. So nitrate is an oxyanion, sulfate is an oxyanion. So this is nitric acid and sulfuric acid. In these acids, the acidic proton is attached to the oxygen. We have carboxylic acids, which were more generally called organic acids. They are organic molecules that contain the carboxylic acid functional group, CO2H. Here, R is just the rest of the molecule. And yeah, those are the main categorizations that SL will go into. And I think even, no, actually the HLs they will encounter a little bit more categorization, but for now, this will work. Actually, no, the SLs will actually. Lastly, you know what? Let me go back on that topic of categorizing acids. The last thing I want to mention is, strong acids and weak acids, but before that, we need to consider acid-base equilibrium, because this will help us distinguish between the two. So, in aqueous solution, the reaction will generally behave like a closed system, and therefore it'll go to equilibrium. Now, a strong acid is an acid whose equilibrium position lies far to the product side. So all of the acid ionizes, so this is the equilibrium that it undergoes in water. So if this is the case, a strong acid is an acid whose equilibrium position lies to the product side and virtually ionizes fully. A weak acid is the opposite. Um, an acid where very little of it ionizes. And for the higher levels, you will be responsible for calculations involving weak acids. However, both are responsible for calculations involving strong acids. So I think we'll go into that next video, but just note that. So those are the last those are some ways that we can categorize acids generally. We can categorize bases similarly, and I'm just going to sort of speed through this section because anything I said about acids can be applied to bases as well. And these are some solutions reactions they undergo. Here's a base ionization equation. They generally take on this form, where B plus H2O forms the conjugate acid and base. Water is amphoteric. When it reacts with the base, it behaves like an acid. Simple ionic compounds that often contain OH are alkali and are basic. Base strength, a strong base is one whose equilibrium lies far to the right side of the reaction, and a weak base is one that whose equilibrium position lies to the very left side. The reaction, it's basically the same thing with acid strength, but that's sort of it. I just said it more or less for the sake of repeating what I said and covering this content. Chemical indicators. A chemical indicator, the AHLs will do a bit more on this, but a chemical indicator is a chemical whose conjugates pairs have different colors to each other, and they can be used to determine the pH of a certain solution, just based on color. So here, for example, an indicator we'll often use is phenolphthalein, which is colorless, and then when it's in acid, it's colorless, and when it's in base, it's pink. And then we have the universal indicators, which are just mixtures of several separate indicators that provide, pH. This is like pH paper. There's just a bunch of different indicators on there, and the color that it spits out will just tell you the pH of the solution. Lastly, well, should I say lastly? Let me just check here. Lastly, we should consider the types of reactions they undergo. They're best memorized in words. So an acid with a metal forms hydrogen gas and a salt. An acid with a hydroxide forms water and a salt. An acid with an oxide forms a water and a salt. An acid and a carbonate forms water, carbon dioxide, and a salt. And an acid with a hydrogen carbonate reacts to form a water, CO2, and a salt. So, you're just going to have to memorize that. The way I sort of reduce the memorizing is that this is actually a redox reaction, so that is that, and it works off the principles of redox chemistry, and if you understand how redox works, then this is pretty simple to derive for yourself. Basically, this is a single displacement reaction. This is higher up on the activity series than this thing is, so therefore it'll displace it and form hydrogen gas and that salt. This should really just say acid with base forms water and salt, generally. Acid with base generally forms water and salt. The salt itself could have, acid-base properties, and for the higher levels, you are responsible for predicting those, but for the standard levels, you're not, so I'll leave it at that. So these two can more or less be memorized as acid and base forms water and salt, and then the only real that's really all you have to remember. And then you only have to remember that if it has carbonate ions, it's an exception, and it forms CO2 in a salt. So you reduce your memorizing from what is essentially 5 things here down to 3, one of which is actually not something you really have to memorize, and it's more conceptual. So you essentially reduce your memorizing from 5 to 2 if you group things together. Like if you group this together as acid and base, if you group this together as acid and carbonate, that reduces your work by quite a lot. Now, I mentioned earlier about how we can categorize acids as strong and weak. How do you actually do that in the lab, though? That's a good question. Now, the way you would generally do this is you could, compare. You could obviously stick pH paper in there, but pH paper is kind of shit. I'll put it that way. Um, and oftentimes too, the difference in pH between a strong and a weak acid. When we go into this, it'll make sense, but a strong acid would generally have a pH of 1, whereas a weak acid would have a pH of 2, which I know that sounds like it's not a big difference, but since pH is logarithmic, that is a big difference, and we'll get into that in the next video. But another way you could do that is you could test for electrical conductivity. The strong acid is more conductive than the weak, and so on and so. And you could use that basis that, okay, how do I tell that's an ionic? You can use that to determine the strength. Um, you could also just stick a pH probe in there. I mean, it'll has the same. It's slightly better than pH paper because it gives you a reading to your tens and hundreds place or whatever. But yeah, I think that's it for this video. So thank you very much for watching.